In this lecture, I'm going to be talking about the derivatives of the 6 trig functions. Our 6 trig functions are sine x, cosine x, tangent x, cosecant x, secant x, and cotangent x. And when we're talking about finding the derivatives of these functions, we're always thinking about x being measured in radians. So when we were looking at the derivative as a function earlier in section 2.8, we sketched what we thought the derivative of sine x looks like. So by seeing where sine x would have a horizontal tangent, and then looking at how the slope was changing between those places with zero slope, we sketched something that looked like this red curve here. And so we had this maybe intuitive idea that the derivative of sine x should be cosine x. But what we want to look at to start with is how we can actually prove that the derivative of sine x is cosine x using the limit definition of the derivative. So let's take a look at this. So we want to find f prime of x if f of x is sine x using our limit definition of the derivative. So f prime of x we know is the limit as h goes to 0 of sine of x plus h minus sine x all over h. Okay. So using the techniques that we have so far, it seems like we won't be able to simplify this, but what we actually have to make use of to get this limit started is a trig identity. So that's what we're going to use first. So we're going to use the trig identity that sine of x plus y, of the sum of two angles, is sine x cosine y plus cosine x sine y. So we're going to make use of that identity in our next step. So we've got the limit as h goes to 0, sine x cosine h plus cosine x sine h minus sine x all over h. Okay. Then we look at this and we see that we can actually do a little bit of factoring. We can't factor something out of this whole numerator, but we do have sine x common to these two terms. So if we pull that out, we've got the limit as h goes to 0 of sine x times cosine h minus 1. And then we have plus cosine x sine h. And these are all over h. Now I'm going to make this over h for the first term and over h for the second term. Okay, so instead of having the sum all over h, we divide each term by h. And what we see is that this limit really relies on knowing what the limit as h goes to 0 of cosine h minus 1 over h is, and what sine h over h as h goes to 0 is. So we're going to take a little closer look at those limits. So let me write one more line down here. So we've got, notice that this limit as h goes to 0 only affects things that have h in them. So this sine x and this cosine x could actually get pulled outside of our limit notation. And we could use our limit laws to look at the limit of this first thing plus the limit of the second thing. So what we have here is sine x times the limit as h goes to 0 of cosine h minus 1 over h plus cosine x times the limit as h goes to 0 of sine h over h. Okay, so the question is, like I said before, what are these two limits equal to? Okay, so let's investigate that a little bit further, starting with sine h over h. Okay, so with some work, which we won't go through all the details of here, but with some work and using geometry, we can show a certain inequality holds for that sine h over h. So we can show that cosine of, let's say, h is less than sine h over h is less than 1. Okay, so with some work, it's possible to get an inequality that holds for this sine h over h. So by the squeeze theorem, we can now say that since the limit as h goes to 0 of cosine of h is equal to cosine of 0, which is 1, and the limit as h goes to 0 of 1 is 1, then, and we say by the squeeze theorem, our limit as h goes to 0 of sine h over h is also 1. Okay, and this is a special limit that could come up in other kinds of limit problems we might be looking at. So we want to memorize this particular special limit. So what about the limit as h goes to 0 of cosine h minus 1 over h? So with this one, we can use some of the techniques that we have seen so far. So although we don't have a square root here, we can still think about multiplying by the conjugate, because we do have some trig identities that will allow us to use. So we can multiply this by cosine h plus 1 over cosine h plus 1, which gives us the limit as h goes to 0 of cosine squared h minus 1. And if you remember your Pythagorean identities, this should look somewhat familiar. So we have this cosine squared h minus 1 over h times cosine h plus 1. So recall the identity of sine squared x plus cosine squared x equals 1. Then we see that cosine squared x minus 1 is equal to negative sine squared x. So we have cosine squared x minus 1 equals negative sine squared x. So what we have here is the limit as h goes to 0 of negative sine squared h all over h cosine h plus 1. Okay. Now we see that one of the pieces that we've already learned about, namely the limit as h goes to 0 of sine h over h, appears within this limit. So this is one situation I was talking about where we can use that previous fact to compute a limit. So we could rewrite this as the limit as h goes to 0 of negative sine h over h times sine h over cosine h plus 1. And we could look at using our limit laws to compute each of those limits separately. So we now know that the limit as h goes to 0 of sine h over h is 1, so that first limit is going to be negative 1. When we do the limit as h goes to 0 of sine h over cosine h plus 1, we know that sine of 0 is 0, cosine of 0 is 1, so that becomes 0 over 2. So this limit turns out to be 0. So I'm a little short on room here, so let me come back up here to the top. It turns out that our limit as h goes to 0 of cosine h minus 1 over h is equal to 0. So this is a second special limit that we can use if it comes up within another limit problem. Okay, so now we want to take these two special limits that we've worked with and go back and finish our derivative for sine x. So we had gotten down to here, and now we can say that our derivative is equal to sine x times our limit as h goes to 0 of cosine h minus 1 over h, which we found, to be 0, plus cosine x here times our limit as h goes to 0 of sine h over h, which we found to be 1. So we see that using the limit definition of the derivative, we have the derivative of sine x is in fact equal to cosine x. Now that we have the derivative of sine x, we're also going to want to look at the derivative of cosine x. And before we do that, we just want to briefly review the trig identities that we've used. We used the addition identity for sine when we were computing the derivative of sine, where we used that sine of x plus y is equal to sine x cosine y plus cosine x sine y. And we used the Pythagorean identity, sine squared x plus cosine squared x equals 1. When we compute the derivative of cosine x, we're going to need the addition identity for cosine, which is that cosine of x plus y is cosine x times cosine y minus sine x sine y. So we want to find the derivative of cosine x using the limit definition of the derivative. So I'm going to say that the derivative of cosine x here is equal to the limit as h goes to 0 of cosine of x plus h minus cosine of x all over h. And then here I'm going to make use of that addition identity. So I have the limit as h goes to 0 of cosine x cosine h minus sine x, whoops, this should be x, sine h here, minus cosine x. So we're going to see that some of the techniques that we're going to use are going to be similar to what we did before. So this is a chance to just see how this process works again. So notice that in this term and this term I have a cosine x, so I'm going to factor cosine x out of those two terms. So we're going to have cosine x times cosine h minus 1 minus sine x sine h. Okay, this is all over h. I know it's going to be all over h. Well, all right, we'll write this in a few steps. So this is all over h. Then I can use the rule that the limit of a difference is just the difference of the two limits. So notice that there's a negative sign here that's coming from the identity for cosine of x plus h, whereas in the previous example we had a positive, a plus sign there because our identity for sine of x plus h involved adding two different terms. So here I see I can write this as cosine x times cosine h minus 1 over h minus the limit as h goes to 0 of sine x sine h all over h here. So again, since cosine x and sine x don't have an h in them, I can treat them like constants. So I'm looking at cosine x, the limit as h goes to 0 of cosine h minus 1 over h, minus sine x times the limit as h goes to 0 of sine h over h. And now I can make use of my special limit rules. I know that the limit as h goes to 0 of cosine h minus 1 over h is equal to 0. That's the value of that limit that we showed before, and I can now use that fact. So this is going to be minus sine x times, the value of the limit as h goes to 0 of sine h over h, which we showed was equal to 1. So now I've got 0 times cosine x, which is 0, minus sine x times 1. So I see that I have negative sine x. So we've shown that the derivative of cosine x is negative sine x. So the derivative of sine is positive cosine, and the derivative of cosine is negative sine. And we saw by doing the proof where this negative sign was coming from. It was coming from this identity here being different than the addition identity for the sine function. Okay, so we've got these two rules and we've gotten a little bit of practice using these limits. So we want to look at finding the derivative of one more function and seeing how using these rules for sine and cosine we can find the derivatives of the four other trig functions. Okay. So here we want to find the derivative of tangent x using what we know about the derivatives of sine and cosine. So again, we know that the derivative of sine is cosine, and we know that the derivative of cosine is negative sine. We've now shown that using the limit definition. So what I want to do here is find the derivative of tangent, but now I'm going to allow the use of these two derivative rules instead of saying we have to go all the way back to the limit definition. Because I can define tangent, or because tangent is defined in terms of sine and cosine, taking the derivative of tangent is the same as taking the derivative of sine of x over cosine of x. So what we're going to see in this example is that all you really need to know are the derivatives of sine and cosine. That's really all you need to memorize. You can always figure out the derivatives of the other four functions because they're based on or defined in terms of sine and cosine. It's certainly faster if you know all of your derivative rules, but we'll see that you can always figure out the derivative rules for the other four based on these two rules. Notice that because tangent is equal to sine over cosine, I can use the quotient rule to find the derivative of sine x over cosine x. So this is, again, good practice using the quotient rule. So that means that we need to have the bottom function here, cosine of x, times the derivative of our top function, which is also cosine x, derivative of sine x is cosine x, minus, let's see, we had bottom function times the derivative of the top, minus the top function times the derivative of the bottom function. So here we're going to use that the derivative of cosine is negative sine x. And this is all over cosine squared x, that bottom function squared. So we see that this is going to give us cosine squared x minus negative sine squared x. So that's going to be plus sine squared x. And so we see we're going to be able to make use of one of our trig identities. So to simplify this derivative, we've now found the derivative of tangent x, but to simplify this and get it into the form that our derivative rule will show, we'll use the trig identity here and write this as 1, since sine squared x plus cosine squared x is equal to 1, is equal to 1 over cosine squared x. And then using what we know about the definitions of our different trig functions, we know that secant x is 1 over cosine x. So 1 over cosine squared x is equal to secant squared x. So we've just shown that the derivative of tangent x is equal to secant squared x. So now we have these 3 derivative rules, and there are 3 more that we need to know. So here's the summary of the 6 derivative rules. We've got the derivative of sine is cosine, the derivative of cosine is negative sine, and the derivative of tangent is secant squared. I would encourage you for these 3 here to do what we just did for tangent. Write secant, write cosecant, write cotangent x in terms of sines and cosines, and use the quotient rule to show these 3 derivative rules. It's good practice with using the quotient rule, and it also may help you remember these different rules. I can also mention a couple other things that might help you remember these 6 rules. Notice that the derivative of all the functions that start with a c, of all the cofunctions of cosine, cosecant, and cotangent, are all negative. So the derivative of a cofunction is always going to be negative. And also notice there's sort of a relationship between the derivatives here of the cofunctions and of the related non-cofunctions. So for example, the derivative of secant turns out to be secant times tangent. The derivative of cosecant turns out to be negative cosecant. So instead of secant, it's negative cosecant, and instead of tangent here, we have cotangent. So the derivative of cosecant, negative cosecant x, cotangent x. We showed the derivative of tangent x was secant squared, and we can show, using a similar process, that the derivative of cotangent x is negative cosecant squared. So instead of secant squared, cosecant squared with a negative sign. Okay, so those are just a couple things that might help you with, remember these rules, but you do need to memorize these rules. Or be able to derive them. Although when in a time situation, you do want to know these rules quickly so that you can use them in a problem. So what I want to do with the other couple of examples in the video lecture is just some examples practicing applying these rules, and we're going to get more practice with derivative rule examples in class, as well as looking at some more trig limits. So here's one example. Here I've got a function g of theta, which is equal to e to the theta times the quantity tangent theta minus theta, and I want to find g prime of theta. Notice that what I have here is a product, so I need to use the product rule. I could multiply e to the theta through first, and but that would end up giving me 2 products, so I might as well just treat this as a product to begin with. So I see that I want to take its derivative, g prime of theta. So using my product rule, I'm going to have the derivative of my first function, which is e to the theta, times the second function, tan theta minus theta, plus the first function, e to the theta, times the derivative of tangent theta minus theta. So here I need to use that the derivative of tangent theta is secant squared theta, and the derivative of theta is 1. So I could just leave it like this. I don't think I'm going to really be able to simplify it all that much if I multiply that out. Okay, so there's one example of applying this rule. Let's look at one more. One other type of problem that we're often asked to find, besides finding the equation of the tangent line, is finding the x values where f has a particular slope. In this case, we want to find the x values where f has a horizontal tangent. So that's going to be finding x where the derivative is equal to 0. So we're going to need to solve that. So first we're going to have to find the derivative of f. Well, f prime of x will be equal to the derivative of x, which is 1, plus the derivative of 2 sine x, which will be 2 cosine x, since the derivative of sine is cosine. Okay, so here we just need to set this equal to 0 now and solve for x. So we notice that this is going to give me negative 1/2 equals cosine x. So this is bringing me back to a trig type problem where I just need to find all values of x where cosine of x is equal to negative 1/2. So if I think about my unit circle a little bit, I know that cosine is negative over here in quadrants 2 and 3. I know that cosine of pi thirds is equal to positive 1/2 from thinking about my triangle. This is 2, 1, root 3. If this angle down here is pi thirds, then adjacent over hypotenuse is 1/2. So I know cosine of pi thirds is 1/2. So where am I going to get negative 1/2? Where I'm going to have to be in this quadrant here. So I see that at 2 pi thirds, I would get a cosine of negative 1/2. Also at 4 pi thirds, I would have a cosine of negative 1/2. And at any multiple of those angles. So I can add 2 pi to either of those angles, and I would get back to the same place where I would have that same cosine. So the complete solution here is that we will have a horizontal tangent at 2 pi thirds plus 2 pi k, meaning any multiple of 2 pi can be added to 2 pi thirds and give us a place where we have a horizontal tangent. And also at 4 pi thirds plus 2 pi k, for k an integer. Because we could subtract 2 pi or we could add 2 pi and we're still going to get to that same location. So that gives us all places where we'd have a horizontal tangent. Okay. So practice working with these derivative rules a little bit. See if you can derive the rules for secant x, cosecant, and cotangent in the same way we did for tangent. Let me know if you have any questions.